Hello guys, welcome back. So today in this video, let's try to solve this lead code question. It says find minimum in rotated sorted array, right? So this is the question. So what they are asking us to do is they'll be giving us an array which looks something like this. If you look at this array, this is not perfectly sorted, right? So if it was perfectly sorted, this array would look something like 1, 2, 3, 4, and 5. But this is not sorted in that way. Instead, this is a rotated sorted array. So what do you mean by rotated sorted array? It means the original array gets rotated certain number of times. For example, in this question, we have this array, and this array was rotated 4 times. So if it after rotating for 4 times, the original array gets changed to something like this, right? So instead of the array being 0, 1, 2, 4, 5, 6, 7, the index, the starting number starts somewhere in the middle, or somewhere at later point in time. So depending on the number of times the array is rotated, this original array is going to be changed, right? So that is what a rotated sorted array means. It's not perfectly sorted from left to right. Rather, a particular portion of the array is sorted rather than the entire portion. So that's a rotated sorted array. All right. So what they're asking us to do is they want us to find the minimum number in this array, right? So given the sorted rotated array of unique elements, return the minimum element of this array. So if you look at this array, straight away anyone can say that the number 1 is the minimum one, right? And in this array, we can say the number 0 is the minimum one. So that is what we need to do. uh, so before jumping into implementations and intuitions, so what is the brute force with which we can solve this question? So the brute force is pretty straightforward, right? You just need to iterate this array from left to right, and keep on checking these numbers. And once you find the minimum array, once you have completed traversing the entire array, you know which is the minimum number, and you just straight away return it, right? So that's a pretty straightforward and brute force way to do this. But then the runtime complexity of this way will be O of n, because you're going to traverse the entire array from left to right, and the runtime complexity increases linearly, which means the complexity increases based on the size of the input. So that is going to be a O of n time complexity. But here in this question, they have said that we need to solve this in O log n time complexity, right? So if it was just O of n, then this wouldn't have been an medium question, right? That would be a very trivial question, and that would be categorized as an easy. Since we need to solve this in O log of n, it's categorized as medium because it's not very straightforward to do that. Okay, so so how can we solve this? So a quick hint, guys, like whenever you see any question which asks us to solve the problem using O log of n time complexity, and you see something like sorted array or rotated sorted array, you could straight away think of binary search approach, right? So that will be your go-to algorithm in such situations. But then if you guys are not aware of binary search, I would recommend pause this video, read about binary search, and then come back here, because we cannot use the binary search straight away here, right? So what is a binary search? So binary search can be applied only when the numbers are sorted in the ascending order. You have one, you have two, right? You have one, uh, you have two, you have three, you have four, you have five, six, seven. So this is a completely sorted number from left to right. So when you have an array like this, then you could use a normal binary search. But this is not a normal sorted array. This is a rotated sorted array. So a normal binary search wouldn't work here. So we have to use an advanced, or an enhanced binary search, or a modified binary search in this case. So let's try to understand what a modified binary searches here. Okay, so let's take the same example that was given, right? So we have what do we have? We have 3 4 5 1 2. So let's plot that here. So we have 3, and then we have 4, then we have 5, then we have 1, and then we have 2. So this is our problem, right? 3, 4, 5, 1, and 2, and we want to find the minimum number here. So the minimum number is 1. So how do we do that? So as usual, we're gonna have, two pointers here. So you have a left pointer and you're gonna have a right pointer, right? So the first thing is you're gonna, find the middle element or the middle index first. So that is completely similar to the way you do your normal binary search. So let's, put the index as well. So this is 0, and this is 1, and this is second index, this is third index, and this is your fourth index. So what we do, we first find the middle element or the pivot element. So how do we do that? We do that by this formula, right? Which is left index plus your right index divided by 2. So here your left index is 0 and your right index is 4. So 0 plus 4 by 2, which is going to be 2. So this is your middle number now. This number 5 is your middle number, right? So now here comes the interesting part. So this is not a normal binary search as we talked earlier. This is a modified binary search. So now you need to know whether your minimum number lies in this left half or in the right half, right? So you have two halves here. So you have this, the number towards the left of your 5 is the first half, and the numbers to the right of 5 is your right half. So now you need to know in which half your minimum number lies. So how do you find that? A simple trick here is you check this middle number with the rightmost number here, right? So here the middle number is 5 and the rightmost number is 2. Okay, let's take a step back here and just visualize this in your mind. If this was a perfectly sorted array, your middle number will always be less than the rightmost number, right? I'll repeat that, guys. So if this was a perfectly sorted array, your middle number will always be less than the rightmost number, right? But then this is not a perfectly sorted array, which means the which means the starting which means the position where the array was shifted, right? That that lies somewhere else. So let me rephrase that a bit. So here we have middle number as 5 and we have the rightmost number as 2, and here if it was a perfectly sorted array, the middle number would have been less than the number 2. But here, since this is not a perfectly sorted array, you see the middle number is greater than the rightmost number, right? So let's write that down here. So here middle number is 5, which is greater than the rightmost number 2. So now this brings us to a conclusion that the position or the place where the array was rotated lies in the right half, right? So if you see this question, the number 1, so this is the index where the array was rotated, right? So you see 3, 4, 5, this is perfectly sorted, and this number, the number 1, is the place where the array was shifted or rotated. So let's consider this number 1 as your rotating point or your shifting point. So whenever you see the middle number which is greater than your rightmost number, then you can know for sure that the position where the array was rotated lies in the right half of the middle number and not on the left half of the number, right? So this is your condition. So if my middle number is greater than the rightmost number, then my minimum number is going to be in the right half. Or let's write it like this, or let's write it in a different way. If my middle number is greater than my rightmost number, then my uh, shifting point or the rotating point lies in the second half, else it lies in the first half. Simple. Let's repeat that one more time. If my middle number is greater than the right number, then your shifting point or your rotating point lies in the second half, which is here. If not, it lies in your left half. So this is all we need to do for this enhanced binary search. All right. So let's try to code it down, and that will make sense. So as usual, you're going to have your left index as 0, and your right index is going to be nums dot length minus 1, and you're going to have your while loop here, which is while left is less than right, right? Then you're going to have your middle index. Let's find the middle index first. This is going to be left plus right divided by 2, and then your middle number is going to be your nums of middle index, right? So far so good. So we have found the middle number. So based on this condition, we have to check if my middle number is greater than my rightmost number, right? So what I'm going to do, I'm going to write that condition here. So if my middle number is greater than my rightmost number here, then I know that my shifting point or the rotating point lies in the second half, right? So now I'm going to shift my pointers here. So my left will become middle index plus 1. Simple, right? If not, if this condition fails, then my shifting point or the rotating point will lies in the left half. So how I'm going to do that? I'll just have a simple else. And here, what I'm going to do is right equals to middle index, right? So simple. Now some of you guys might wonder, why am I not putting middle index -1 and I'm putting just right equals to middle index, right? Because this number 5, this itself could be your smallest number, right? I have to take that number also into account. uh, in the first condition where middle number is greater than the rightmost number, I know the only possible answers are 1 and 2, and 5 will not be an answer because 5 is already greater than 2, so this cannot be a smallest number. So the possible answers are either 1 or 2. So that is why I put my left equals to middle index plus 1. So I start searching from here. But if not, if I go to the else part, if this middle number is less than the rightmost number, then I have to search in the first half. But when you search in the first half, you should also take this middle number into account. You just can't, simply ignore this number. This number also could be a minimum number if you're going to the else loop here, right? So if you're putting middle index -1, then you will be searching only for 3 and 4, and you will be ignoring this middle number. So that is an edge case that you have to take care here. So that is the reason I put right equals to middle index. Hope that is making sense. If it is not very clear, let me know in the comments. I'll try to explain a bit more clear. All right. So once this is done, when your left becomes equal to right, then your while loop will break, and that number will be your smallest number. So what I do here is I'll just return nums of left, and this will be my smallest number. So let's try to run this. Yes, it got accepted. So since left equals to right, it doesn't matter whether you put nums of left or nums of right, both both is going to work. So if I use nums of right, even that is going to work. All right, so let's submit this. All right, this got submitted. So yeah, so that is all, guys. Hope this was clear. If it is not clear, let me know in the comments. I'll try to explain a bit more. So before I just jump off, uh, just make sure that your while loop is always left is less than right. So when you go with a normal binary search, you would have done left less than or equal to right. But then in this problem, we are using left is less than right because we are not trying to search for a particular number here, right? Because if you look at the normal binary search, the question would be something like this. They would have given you a perfectly sorted array, and they would have given you a target. So the objective for you is to find that target number in that array. But this question doesn't ask you to find any target as such. It always asks you to find the smallest number. So that smallest number can be 0, that could be 10, that could be 100, or that could be 1000 as well, right? They haven't given you a fixed target. So if they would have given you a fixed target in a normal binary search, you would have used left less than or equal to right. But here you just need to find the smallest number in this rotated sorted array. So you keep on shifting this pointers left and right, and you narrow down or you shrink your window till you reach the last element, which is going to be your smallest element. Yep. So that is one thing to keep in mind. All right. Thanks, guys. See you again in another video. Bye bye.